we have our first talk by Dr. Sriram Somasundaram on energy storage and overview. I would like to give a brief description, a brief profile of this work. As a managing director of the OSG India office, Dr. Sriram Somasundaram oversees OSG's operations and technology teams, helping them to improve their problem-solving skills, become accountable and collaborate across the different functional areas and geographies. Before joining OSG, Sriram worked at the Pacific Northwest National Laboratory for over 28 years, with expertise in areas of energy efficiency, economic assessment of cogeneration systems, thermal energy storage, and new technologies for creating energy efficient infrastructures. Dr. Sriram received his PhD in Mechanical and Aerospace Engineering from Case Western Reserve University, Cleveland, Ohio, after which he taught at Texas A&M University, College Station, Texas, from 1981 to 1989. He got his BTech degree in Aeronautical Engineering from IIT Madras in the year 1976. Now, I request Dr. Sriram Somasundaram to please deliver his talk. Thank you.
Thank you very much for that introduction. Can I share my screen? I think the host has to let me do that.
Yes, sir, you can share your screen, sir.
Okay, thank you. Can you see the screen with the title slide, Energy Storage and Overview? Yes? Hello?
Yes, it is visible. Can be seen.
Thank you. Thank you very much. So let me begin my talk by saying how much I appreciate the invitation. Professor Srinivas Pendyala and Satyanarayana Kuchibhatla, a local entrepreneur in Hyderabad. We are mutual friends, and that's how we got connected. So this talk is going to be an overview of both electrical and thermal energy storage. Most of the thermal energy storage work that I did back in the 90s and early 2000s were in the areas of thermal energy storage in using phase change material and solar towers and so on. But I also wanted to give you an overview of the electrical storage mechanisms for today's talk so that we cover both areas. What is energy storage? So it is simply the capture of energy produced at one time for use later to reduce imbalances between energy demand and energy production. And as our Vice Chancellor was stating earlier, the most common form of energy storage is the pumped storage hydroelectric form, where water is pumped to a height above storage level and run through the allowed to flow through the turbines, thereby producing power when it flows down from the height to a lower level. There is also the technologies of flywheel energy storage, compressed air energy storage, capacitor or supercapacitor, superconducting magnetic energy storage or SMES, the electrochemical forms of storage, as he mentioned also, which are comprised of flow battery or rechargeable battery. There is also the molten salt storage for storing thermal energy from solar energy, and ice storage, air conditioning for running the air conditioning during the day, where the ice storage is powered up during off-peak times when the electricity costs are cheaper. And then there is the whole field of seasonal thermal energy storage, where chill energy can be stored from in the winter for use and recovery and use in the summertime for cooling the buildings. At the same time, the aquifer where the chill energy is stored can be used to store heat during the summer as a hot water, which can then be recovered and used for heating the buildings during the winter season. So this form of storage, which crosses across the seasons, is called a seasonal thermal energy storage. The comparative estimates of total current installed capacity are given here on this figure. This is only for an illustrative purpose. There's no relative size of some of the storage capacities. But as you can see, the pumped hydro is the largest source of storage, with more than 127,000 megawatts electric installed worldwide. Compressed air energy storage is next, with about 440 megawatts installed, followed by sodium sulfur batteries at 316 megawatts, and all other remaining sources worldwide total less than 85 megawatts combined. And those include lead acid battery, nickel cadmium battery, flywheels, lithium ion battery, which are commonly used in your smartphones and laptop computers, and redox flow battery, which is gaining popularity more recently, but it is right now only at about less than 3 megawatts. This chart shows the relative positioning of the electric energy storage technologies, where you have the system power ratings along the x-axis, which is the module size or the storage size. And plotted along the y-axis is the discharge time at rated power. And the y-axis begins with seconds to minutes to hours. And the capacity along the y-axis is ranging from 1 kilowatt all the way to 1 gigawatt, which is 1,000 megawatts. As you can see, in some of the lowest rated storage are the batteries and supercapacitors. And then which are usually the uninterrupted power systems, the backup power, the inverter, and high power quality, and where the high power quality is needed is on the leftmost side of the chart, the yellow region. The green portion of the chart shows some of the transmission and distribution grid support for load shifting purposes. And those storage technologies are mostly in the flow batteries, sodium sulfur batteries, advanced lead acid battery, the sodium nickel chloride battery, lead acid battery, and high power supercapacitors, as well as SMES, the superconducting magnetic energy storage that I talked about earlier. Also, the high power flywheels fall in this category as well. The compressed air energy storage case, or the pumped hydro, is all the way to the right of the chart, where you need bulk power. And those are some of the larger installations worldwide. And most of them cover the basic power storage in very large installations in different countries of the world. So, by the way, I forgot to mention in the last slide that the reference that I point out on top of the chart, top of the slide, I have listed all these references on another slide deck that I sent out to Professor Peñala 2 days ago. I hope he has sent that out as part of your reading material. So you can, at your leisure, go and reference those sources for more information. So let's begin with the mechanical forms of storage. We already talked about hydroelectric dams to a certain extent. These are operated to provide electricity during peak demand times, like pump storage, but without the pumping loss. One of the most efficient forms of energy storage, and it is also the most often used form of storage. Hydroelectric turbines have a startup time on the order of a few minutes, unlike some of the power plants which need a few hours to be fired up and brought to full capacity. Pumped hydro is the largest capacity form of active grid energy storage, available with energy efficiency varying from about 70% to 80%, with claims of up to 87% efficiency. At times of low electrical demand, excess generation capacity is used to pump water from a lower source to a higher reservoir. So when demand grows, water is released back into a lower reservoir through a turbine. And that's how you generate electricity. Other forms of mechanical energy storage are compressed air energy storage, CAES, which uses surplus energy to compress air for subsequent electricity generation. Compressed air is stored in an underground reservoir, such as a salt dome. CAES plants can take in the surplus energy output of renewable energy sources as well, to be used later. Compression of air produces heat. Expansion requires heat. And so if the heat can be stored and used during expansion, efficiency improves considerably. Air storage can be adiabatic, diabatic, or isothermal. Compression air can be used to power vehicles such as mine locomotives, to operate locomotives to carry coal or other materials up and down a mine. Other forms of mechanical storage include flywheel energy storage, which works by accelerating a rotor, a flywheel, to a very high speed, holding energy as rotational energy or dynamic energy. Most flywheel energy systems use electricity to accelerate and decelerate the flywheel. Rotors are made of high-strength carbon fiber composites, suspended by magnetic bearings and spinning at speeds from 20,000 to 50,000 revolutions per minute, RPM, in a vacuum enclosure. They can reach maximum speed in a matter of minutes. The flywheel systems is connected to a combination electric motor generator to generate electricity. Flywheel energy systems have relatively long lifetimes, high specific energy, measured in terms of watt hours per kilogram or kilojoules per kilogram. The range is 100 to 130 watt hours per kilogram, or 360 to 500 kilojoules per kilogram, and high power density as well. The solid mass gravitational form of energy storage changes the altitude of solid masses, which can store potential energy and release the energy when needed. Energy released as little as 1 second, in as little as 1 second warning to balance load surges in an electricity grid. The electrochemical forms of storage are in the common forms of battery that you are all, of course, used to now. In the form of rechargeable battery, which are used in laptops and computers and smartphones, comprises of one or more electrochemical cells, also known as a secondary cell, because its electrochemical reactions are electrically reversible. So as it discharges, it releases electrons where you lose power. And when you recharge it, you charge it with using either backup power or electric grid, and it regains charge. The batteries come in many shapes and sizes, ranging from button cells that are used in watches to megawatt grid systems. Rechargeable batteries have lower total cost of use and environmental impact and low environmental impact than disposable batteries, where the batteries are not rechargeable and so have to be disposed of carefully when they run out of charge. Even though the initial cost of the rechargeable battery is high, but because it can be recharged often and very cheaply and used frequently and many more times than initially used. Lead acid battery is another form of electrochemical storage, where lead and lead sulfate electrodes immersed in a dilute sulfuric acid electrolyte are commonly used in cars and trucks, for charging automobile engines. Nickel cadmium battery, NiCd, is another form of electrochemical storage, but it is almost completely replaced now by nickel metal hydride battery, NiMH, which are also used in some of the hybrid cars these days. I remember the Hyundai hybrid car used the nickel metal hydride battery. Because cadmium use has been banned and because of its toxicity. Lithium-ion battery, as I told before, used in most consumer electronics goods, has one of the best energy to mass ratios and a very low self-discharge when not in use. And that's why the more recent lithium-ion batteries in smartphones last almost a day or several days without recharging. Lithium-ion polymer battery are light in weight and can be made in any desired shape to fit the need of an appliance. Flow battery, as I mentioned earlier, works by passing a solution over a membrane where ions are exchanged to charge or discharge the cell. The cell voltage varies from 1 volt to 2.2 volts. Storage capacity depends on the volume of solution. Technically, this is akin to both a fuel cell and an electrochemical accumulator cell. And commercial applications are for long half-cycle storage, such as backup grid power. Supercapacitor is another form of electrochemical storage. It's also called electric double-layer capacitors or ultracapacitors. These are a family of electrochemical capacitors that do not have conventional solid dielectrics. Supercapacitors bridge the gap between conventional capacitors and rechargeable batteries. They store the most energy per unit volume or mass or energy density among capacitors. Shorter charge and discharge cycles, they tolerate many more charge and discharge cycles than batteries. Applications of this type of supercapacitor include low supply current for memory backup in static random access memory, power for cars, buses, trains, cranes, and elevators, including energy recovery from braking, short-term energy storage, and burst mode power delivery. Redox flow batteries are the next technology that I'm going to talk about. There is a, in this form, energy is stored in electrolytes instead of electrodes. They have emerged as prime candidates in the development of large-scale grid-connected energy storage systems because they offer very long cycle life, high energy efficiencies, as well as low costs for applications requiring high energy to power ratios. Several different flow battery technologies have been under development over the past 30 years, but of these, only the vanadium redox flow battery that was pioneered by the University of New South Wales, Australia, and the zinc bromine battery first developed by Exxon are currently under consideration for large-scale grid integration. To date, more than 30 medium to large-scale flow battery installations in Japan, Europe, United States, and China have demonstrated the technical benefits of flow batteries in a range of off-grid and grid-connected applications. But the current challenge is to reduce costs for widespread commercial penetration. The next slide is a schematic diagram showing the redox flow battery and the way it operates. So the current collector through this common cell flows into the energy storage tank or anode energy storage tank, whereas there's a porous separator between the two fluid streams where the cathode energy is stored in the red tank. And across the two electrodes, cathode and anode, the current flows through the discharge mechanism here, shown here. So the pumps are used to pump the fluids through the medium and generate power through that mechanism. A flow battery in is a type of electrochemical cell where chemical energy is provided by two chemical components dissolved in liquids that are pumped through the system on separate sides of a membrane. The dashed line here shows the membrane. Is an ion exchange occurs through the membrane while both liquids circulate in their own respective space. Cell voltage is chemically determined by the Nernst equation and ranges in practical applications from 1 to 2.43 volts. Other forms of electric vehicle storage or EV storage are shown here. 4 new energy storage technologies are powering the EV revolution. The true cost of electric vehicle ownership should include fuel and maintenance of the electric drive, as well as the price of the vehicle. Even though the first cost of the electric vehicle is high, but because the cost of fuel, which is electricity in this case, through batteries, and maintenance of electric motor or electric drive is comparatively very low compared to a gas powered engine, the overall total cost of ownership of an electric vehicle is lower than the gas powered vehicle. And it is coming down every year. Now that Tesla has commercialized the technology and has sold thousands of vehicles this past year, the costs are continuously coming down. And there are more manufacturers coming into the market. And in the future, there should be even more cars available using electric energy for its locomotion. The emerging battery technologies for electric vehicles are replacing cobalt and nickel in lithium-ion batteries with iron or manganese. A solid-state battery, which is just coming into the fore, being developed by QuantumScape Corporation, whose CEO is Jagdeep Singh. And this company is also being actively supported by Bill Gates of Microsoft. This is based on a solid, non-flammable material. And instead of using flammable liquid electrolyte, is a lot safer, and because it does not use a non-flammable material. A multivalent battery, instead of using lithium ions, would use materials such as magnesium, calcium, or possibly aluminum. And these would be much smaller and more powerful batteries. Sodium-ion batteries could come in at half the cost of lithium-ion batteries for utility scale storage using renewable energy sources instead of natural gas or even compressed natural gas for fleets of electric vehicles. The reference here is the 4 new energy storage technologies to power the EV revolution on the website cleantechnica.com. So this concludes the portion on the electric storage technologies. I'd like to ask if there are any questions or doubts or clarifications people would want at this point.
Right now, there is one question, sir.
Okay.
Of course, slightly away from what you are discussing till now, but I suppose it is Mr. Anantesh Rao K. He says, good morning, sir. Till what temperature wax can be used as thermal energy storage using solar energy?
Yes. So I'm going to be talking about this in the next half of the presentation.
Yeah.
So hopefully I'll be answering his question.
That was the only question, sir. You can continue.
Okay. Yeah. Thank you. So yeah, so in the future, I mean, people can post their questions here on the discussion Q&A section, which we can monitor. So let me also check to make sure the slides are visible and my voice is audible to everybody and clearly.
Yes, sir. It's clearly visible and audible as well, sir. Thank you.
Very good. Very good. Yeah, it's always a challenge in some of these large gatherings, but I'm glad it is working well. And I'm glad that, so I'm showing 87 participants online. So that's a very good number. So let's begin with the thermal energy storage. So this of course is using, storing chilled water, chill energy, ice, and as well as heat, and in the form of molten salts or hot water or steam, either in aquifers, either in storage tanks, and so on and so forth. Of course, you can also have other media, storage media, such as glycol solutions or non-corrosive substances used to store heat. And all of this is either from the exhaust stream of a gas turbine, where heat is released to the atmosphere. And instead of releasing the heat to the atmosphere, some of it can be stored in high temperature water or steam, high pressure steam, for later use and later production of electricity. So the idea here, and unlike the electrical form of storage in batteries and other mechanical means, is to store the thermal stream as well in different forms for either later generation of electricity or for use as thermal energy itself for drying substances or materials and processing materials as in a chemical plant and so on. So this whole field of thermal energy storage is at relatively increased efficiencies compared to electrical energy storage, and also requires less cost and can be utilized in different buildings, including residential buildings and commercial buildings, and not necessarily only at the grid level or transmission and distribution level storage. So thermal energy storage is achieved with widely different technologies as well. Depending on the specific technology, it allows excess thermal energy to be stored and used hours, days, months later, at scales ranging from the individual process or a building or a multi-user building or a district level where you have a cluster of buildings or a town or a downtown. So in Europe, most of the winter heating is achieved by what is called district heating systems, where either hot water pipes or hot air ducts are run through buildings, and the hot water is supplied from a central system throughout the town. And that is at very increased efficiency and reduced cost, because you don't have to have, or you can afford to have larger systems, and the volume of water use and is so large for such a large number of buildings over the whole region or a whole town, that the cost multiple is much lower. Usage examples of thermal energy storage are balancing of energy demand between daytime and nighttime. These are called diurnal storage. Storing summer heat for winter heating, or winter cold for summer air conditioning, as in seasonal thermal energy storage. Storage media include water or ice slush tanks, masses of native earth. So you can, as I mentioned before, aquifers or large masses of water can be stored, energy can be stored in large masses of water in an aquifer, deep underground, or a bedrock accessed with heat exchangers by means of boreholes, deep aquifers contained between impermeable strata. Or you can have it in shallow lined pits filled with gravel and water and insulated at the top, as well as eutectic solutions and phase change materials. So the phase change materials are mostly latent form of storage, heat storage, where the material changes phase. So a solid material will melt, thereby absorbing the heat and change into liquid form. And when you discharge the liquid material to release the heat, it freezes back into a solid form. So that, as opposed to the sensible heat where simply there is a temperature increase in the liquid storage medium, this is called a phase change material. Two of the references that I used for this, or you can look up at leisure, are given at the bottom of the slide. And like I mentioned before, these are also listed in the slide deck titled reference sources. So thermal energy storage, other sources of thermal energy storage include heat or cold produced with heat pumps from off-peak, lower cost electric power, a practice called peak shaving, where when usually the electric grid or the electric generation company will offer electricity at cheaper rates during so-called off-peak periods, which are usually nighttime or the shoulder periods of the day, early morning or late evening, late night. And so you can run your compressor to form ice for storing or cold water for storing for later use using the off-peak electricity. Heat from combined heat and power plants. These are so-called the cogeneration plants, where, like I said before, if you have a bottoming cycle plant, you can run the gas turbine for primary electric generation using fuel generated flue. And then once the exhaust has been expanded through the gas turbine, the temperature is lower, but still hot enough for producing steam for storage for later use. Heat can also be produced by renewable electrical energy that exceeds grid demand, and also using waste heat from industrial processes. Heat storage, both seasonal and short-term, is considered an important means for cheaply balancing high shares of variable renewable electricity production and integration of electricity and heating sectors and energy systems almost or completely fed by renewable energy. So let's look at the next two slides. There was a question about wax systems, which is another form of phase change material. Here we are talking about a molten salt mixture, which is used in solar powered plants where the temperatures are much higher than what the wax system uses. So these molten salts are those that melt at 430 degrees Fahrenheit and is kept liquid at 550 degrees Fahrenheit on up. So this is a mixture of 60% sodium nitrate and 40% potassium nitrate, commonly called saltpeter. This is stored in an insulated cold storage tank at 550 degrees Fahrenheit. The salt is then pumped to the top of the tower where concentrated sunlight heats the salt mixture in a receiver to 1050 degrees Fahrenheit. That hot salt is then used or stored in a hot storage tank until when you need the power, either during nighttime when the sun has gone down, or when there is a need for peak power beyond the hydroelectric dam or other sources of or nuclear energy plant, where you can use this to cover the peaks. The receiver is a series of thin-walled stainless steel tubes. The heated salt then flows back down to a second insulated hot storage tank. The size of this tank depends on the requirements of the utility Tanks can be designed with enough capacity to power a turbine from 2 to 12 hours. When electricity is needed from the plant, the hot salt is pumped to a conventional steam generating system to produce superheated steam for a turbine or a generator. As an example of their size, tanks that provide enough thermal storage to power a 100 megawatt turbine for 4 hours would be about 30 feet tall and 80 feet in diameter. Studies show that the two-tank storage system could have an annual efficiency of about 99%. You could also have a single tank system with divider plate to hold both cold and hot molten salt using across a divider plate. That will reduce the cost because they're both in the same single tank. It is more economical by achieving 100% more heat storage per unit volume over the dual tank system, as a molten salt storage tank is costly due to its complicated construction. This diagram shows the receiver, the solar receiver that is receiving the heat through from a heliostat focused on the receiver disk, which then heats the salt that is passing through the tubes within the receiver. The salt itself is pumped from a low temperature storage tank on up through the receiver back down at 1050 Fahrenheit to a hot salt storage tank. This is then pumped as needed when pumped out of the tank when needed to produce steam in a heat exchanger, and the steam generator then runs the steam through a turbine generator to produce power. The exhaust steam or the low temperature steam is rejected through a cooling tower, and the condensate or the feed water comes back down into the heat exchanger to produce more steam. This is a simple diagram of a solar powered tank storage as well as a steam production system. This was the design of a solar tower 1 and solar tower 2 in the US in California, in the deserts of California region called Barstow. And this plant was designed and maintained by Sandia National Laboratory. And Tom Mancini was one of the primary investigators of this system. He's still doing some consulting now that having retired from the national lab, but he is one of the primary contributors to this technology. Solar power tower, also known as central tower power plants or heliostat power plants. The technology is now used in several other countries, even though the solar power itself has been shut down for a few years since its launch and primary use. The technology has now been shifted to Europe and Spain and other countries, and similar technologies are used there. I have a few diagrams on the next slide. This type of solar furnace using a tower to receive the focused sunlight uses an array of flat or movable mirrors called heliostats to focus the sun's rays upon a collector tower or the target. Concentrated solar thermal energy is seen as one viable solution for renewable pollution-free energy source and storage. Early designs use these focused rays to heat water and use the resulting steam to power a turbine. Newer designs use the salt mixture that I talked about here. They can also use liquid sodium, and where it is available and where it can be stored in a storage tank. Of course, the sodium system has to be very carefully handled, and at very high temperatures, they are very dangerous and flammable. These working fluids have high heat capacity, but which can be used to store energy before using it to boil water to drive turbines. These designs also allow power to be generated when the sun is not shining or the night times. This shows several installations around the world where you have a parabolic trough of mirrors on the left, which can move or which can be moved or rotated to track the sun. So as the sun moves across the sky, the mirrors are focused on it in a slower revolution path. And this Solana project is in Arizona and built in 2013. Gemma Solar Power Plant in 2012, which you can see the central tower almost illuminated to white glow because of the focused sunlight. The A1 Power Facility designed and built in 2013, also in Arizona, is very similar, where you have this disk illuminated by solar energy. Sorry. The Gemma Solar, I forgot to mention, is a plant in Spain, achieved a first by continuously producing electricity 24 hours a day for 36 days. This plant on the left. The Solana generating station had the largest parabolic trough in the world when commissioned in 2013 in Arizona. Can store 6 hours worth of generating capacity in molten salt. Phase change materials in a shape stabilized medium is part of this research conducted in 2020, where you have shape stabilized phase change material to avoid transport or leakage of the phase change material during its charge and discharge cycles, so that it is kept in matrices and kept in its form, and so there is no leakage or dispersal of the medium. The findings of this study of the 5 types of mesoporous matrices investigated, all except MCM41 yielded shape stabilized PCM or phase change material with thermal stability above 500 degrees C and 2 melting and 2 crystallization events. The FDU12 and mesocellular foam silica were found suitable matrices for sodium nitrate and potassium nitrate molten salts, which could be used to tailor the heat storage distribution and tailor the temperature range. Phase change salts are also used for storage. This diagram shows where you have a core sodium nitrate, which is heated to about 300 degrees C, and the gap between the shell layer and the sodium nitrate core becomes void for the PCM material to expand into the shell. And so the sealed shell contains the PCM in its core or in its interior without having the material disperse away out of the shell. So this constant expansion and contraction of the salt is enabled by this shell layer or the intermediate layer between the two, between the shell and the salt itself, salt core itself. Mathematical models used in this study indicate that over 90% of the salt in the capsules undergo phase change, improving energy density by over 50% from a sensible only thermal storage. Another advantage of this method is that it requires only a single tank, as opposed to the 2 tanks used in a sensible heat storage, thereby reducing the cost from a nominal $27 per kilowatt hour thermal to $16 per kilowatt hour thermal, and coming close to the sunshot goal for thermal storage of $15 per kilowatt hour thermal. So this reference is also in your list. Adsorption or sorption solar heating. This form of storage is also very efficient and has been used more recently using synthetic zeolites such as Lindy 13X with water adsorbate has garnered much academic and commercial interest recently. So this is particularly of use for low-grade solar and waste heat storage. Several pilot projects have been funded in the EU from 2000 to present. The basic concept is to store solar thermal energy as chemical latent energy in the zeolite. Typically, hot, dry air from flat plate solar collectors is made to flow through a bed of zeolite such that any water adsorbate is driven off. Storage can be diurnal, weekly, monthly, or even seasonal, depending on the volume of the zeolite and the area of the solar thermal panels. When heat is called for during the night or sunless hours or winter, humidified air flows through the zeolite that then absorbs the heat, and as the humidity is adsorbed by the zeolite, heat is released to the air and subsequently to the building space. This form of thermal energy storage with specific use of zeolites was first taught by Guerra in 1978. Advantages over molten salts and other high temperature TES systems include the fact that the temperature required is only the stagnation temperature typical of a solar flat plate thermal collector, and if the zeolite is kept dry, the energy is stored indefinitely. Because of the low temperature and because the energy is stored as latent heat of adsorption, thus eliminating the insulation requirements of a molten salt storage system, costs are significantly lower. Heat storage in tanks or rock caverns. We talked about compressed air storage. Here you have heat storage in a rock cavern or storage tanks. Again, some of the systems in Europe estimate that you can have 11.6 gigawatt hours of capacity and 120 megawatt of thermal output for its 260,000 meter cubed of water cistern underground, fully charged or discharged in 4 days of capacity, operating from 2021 to offset days of peak production or demand. The gigantic cavern heat storage facility to be implemented in Mustikama in Helsinki, Finland. Large stores are widely used in Scandinavia to store heat for several days, to decouple heat and power production, and to help meet peak demands. Interseasonal storage in caverns has been investigated and appears to be economical as well. This is again a schematic of how the heat and chill can be stored underground in separate tanks and then pumped out during times of need through the building systems or the district heating or cooling systems. There are similar systems in the US as well. In a lot of university campuses, they use the either the football field or athletic field to have pipes underground and run steam through it to keep the ground warm or to defrost snow that falls on it, or also to heat and cool the buildings in the campus. Heat storage in hot rocks or concrete. Let me show you the diagram in the next slide. Here you have wind energy stored in the form of heat in the caverns or in the rock, and recovered during time of need using generators. So this Siemens system has built they have built a 130 megawatt hour thermal storage plant near Hamburg with 750 degrees C in basalt, or the rock, heated by electricity from wind, and 1.5 megawatt electrical output from a steam turbine for up to 24 hours from storage. This plant was commissioned in 2019 and has been in operation since. So you could store heat generated either from electricity or waste heat, as we saw in earlier applications. A similar system is scheduled for Soro, Denmark, where with 41 to 58% of the stored 18 megawatt hours of heat returned for the town's district heating system, and 30 to 41% returned as electricity. This earlier bullet talks about a system in Germany that has received international attention and uses it to supply 570 houses with around 50% of their heating and hot water needs. Aquifer thermal energy storage I talked about earlier. This one system, which used heat storage in the University of Minnesota campus, was monitored by us as part of a contract with the US Department of Energy. And so I'm quite familiar with this system, which we helped monitor in the 80s and early 90s. And when the contract ran out, we stopped monitoring it. I don't know if the campus still has it in operation, but while it worked very well, very efficiently. And they were very happy with the efficiency and effectiveness of heat availability. So they would use the aquifer below the campus, underground below the campus area, and would recover heat in the winter and store the heat in the summertime. So the overall efficiency was 66%, and they were able to get 4.13 gigawatt hours of energy stored in the aquifer was to be able to be recovered. So this LT3 is the long-term cycle of storage 3. That is the third long-term cycle. So every season or every winter, they would recover it, store the cold water in the aquifer. In the summertime, they would pump it up, heat it up, and store it back for winter use. Salt hydrate technology uses organic salts or ionic liquids. Compared to lithium halide-based absorbents, they are less problematic in terms of limited global resources, and compared to most other halides and sodium hydroxide, they're less corrosive and not negatively affected by CO2 contaminations. These are organic salts and so-called ionic liquids. These have also been shown to be very effective. The highest energies of dilution observed in these series were obtained for the acetate-based salts, ionic liquids, which underline their potential as working fluids in sorption-based thermal energy storage systems. Thermal energy storage in combined heat and power systems. Thermal energy storage technologies heat or cool a storage medium, and when needed, deliver the stored thermal energy to meet heating or cooling needs. So these are typically these are used in power plants, as well as wherever there is cogeneration of power and heat. And the waste heat can be stored either in form of salt or hot water or waxes. So there was a question earlier about wax systems, where the melting point is usually in the 80 degrees Fahrenheit or 35, 40 degrees centigrade. And the molten wax then refreezes at its melting point. So the temperature range of operation of these systems is very limited. And we talked about some of the higher temperature ranges using the salt storage or the high temperature liquids, or high pressure steam, where the temperatures of or temperature ranges of storage are much higher. So waxes can only be used in building envelopes, building walls, where the temperature range is typically much lower in terms of space heating and space cooling systems. And we'll talk more about those systems actually in the on the Thursday morning session, when we talk about building envelopes and phase change materials in building envelopes. This slide is basically talking about TES, thermal energy storage systems used in commercial buildings, industrial processes, where I talked about storing steam for later use in the chemical plant for either drying materials or processing materials, or in district energy installations where you run the steam through building complexes or downtowns of cities and so on. And basically it delivers stored thermal energy during peak demand periods, that is during the daytime when occupants are in the commercial building, and for comfort, heating and cooling. So running the cooling system or the heating system from storage reduces the peak energy use of electricity, where when I said during the daytime of 9 a.m. to 6 p.m. is the maximum cost of electrical energy. So you would want to save that on-peak energy use, and you do that by using chillers and ice storage systems during the daytime, and charge it up during the nighttime. So TES systems are often integrated with electric or absorption chillers to reduce peak electricity costs. In the case of new construction, to reduce capital costs by optimizing chiller size. Right sizing equipment or correctly sizing these equipment improves overall efficiencies for heating or cooling plants, thereby reducing total energy use and carbon dioxide emissions. Thermal energy storage technologies can support sites that have either renewable or fossil power generation, including combined heat and power installations. With CHP, TES can help optimize equipment size by reducing the required peak CHP thermal capacity and increasing the annual combined heat and power usage. TES can also provide turbine inlet cooling for gas turbines. For those of you who have learned about gas turbine technology, you know that the inlet air has to be at a certain optimum temperature for it to deliver maximum efficiency. So in gas turbine installations in very hot climates, as in Saudi Arabia or Middle East and so on, they have a turbine inlet air cooling system installed before the air enters the gas turbine. So for cooling the air, you use a heat exchanger and either an ice storage or a electric compressor to cool the air before it goes into the turbine at the optimum temperature. This then produces a maximum output in the combined heat and power system. The exhaust gas from the combined heat and power plant is then used to store or used in an absorption chiller to produce chilled water as well. So there is a full cycle of a closed cycle of operation of chilled water to cool the air and then be produced from the exhaust stream of the gas turbine itself. So I have published several papers in this area in the late 80s, early 90s of my work, and you can look them up in the on the internet. These are a couple of papers that I came across for showing low-cost solution to grid reliability problem, where you have 100% penetration of intermittent wind, water, and solar for all purposes that is talked about. This particular study done in 2015 addresses the greatest concern facing the large-scale integration of wind, water, and solar into a power grid. The high cost of avoiding load loss caused by the variability and uncertainty of these renewable energy sources. It uses a new grid integration model and finds low cost, no load loss, non-unique solutions to this problem on electrification of all US energy sectors. And as I mentioned earlier, there is a big move to electrifying not only the grid and buildings, but also now the transportation sector and the industrial manufacturing sector, of course. So you need a lot more energy stored and utilized at a later time. And so these larger systems are designed to bring the cost down as well. So solutions are obtained by prioritizing storage for heat in soil or water and cold in ice and water. And electricity, of course, in phase change materials, pumped hydro, hydropower, and hydrogen. And using demand response for utilizing the electricity at optimum times. No natural gas, biofuels, or nuclear power are needed. The resulting 2050 to 2055 US electricity social cost for a full system will be down to 11.37 cents per kilowatt hour, which is much less than for fossil fuels. These results hold for many conditions, suggesting that low-cost, reliable 100% renewable energy systems should work in many places worldwide. This other paper also talks about smart energy systems for coherent 100% renewable energy and transport solutions. The hypothesis of this paper is that in order to identify least cost solutions of the integration of fluctuating renewable energy sources into current or future 100% renewable energy supplies, one must take a smart energy system approach, focused on merging the electricity, heat, and transport sectors in combination with various intra-hour, hourly, daily, seasonal, and biannual storage options to create the flexibility necessary to integrate large penetrations of fluctuating renewable energy. To enable this, the smart energy system must have several appropriate infrastructures for the different sectors of the energy system, which are smart electricity grids, smart thermal grids, which are district heating and cooling systems, smart gas grids, and other fuel infrastructures as well. It enables fluctuating renewable energy, such as wind, solar, wave energy, and low-value heat sources to utilize new sources of flexibility, such as solid, gaseous, and liquid fuel storage, thermal storage, and heat pumps and battery electric vehicles. So you can establish these infrastructures type systems to cover the entire range of uses and applications. So feasible use of bioenergy than the current types allow. So this can potentially pave the way to a bioenergy-free 100% renewables energy and transport system. So the last slide is more of these, more reference sources for further reading. And these are all included in the reference source slide deck that I talked about earlier. And like I mentioned earlier, Tom Mancini has a TR Mancini Solar Consulting now, is one of the primary investigators in the concentrated solar power technology field. He used to work for Sandia National Laboratory, a fellow laboratory man of mine, and located in Albuquerque, New Mexico state. So that concludes the session, the overview session for now.
Yes, sir. So, yeah, thank you, sir.
Are there any
Thanks.
questions or
Yeah,
discussion?
we'll have a look at the questions, sir. Few people have raised their hand.
Okay.
Mr. K. Sudhakar, Mr. Aksar Ali, Mr. Prabhakar, Mr. Mutwel. If you have any questions, can you please post them in Q&A? Okay. Yeah, we have the question from Mr. K. Sudhakar. How do you foresee the future of TES for renewable energy applications?
Yeah. So I'm not sure what you mean by how do I foresee. I definitely see a future for thermal energy storage because, like I said before, in order to reduce wastage and exhausting the exhaust stream, or releasing the exhaust stream from a gas turbine or a high pressure steam turbine application, in order to recover as much heat from the exhaust source as we can, we absolutely need to convert it to any form of steam, whether it is low pressure steam or even hot water, for use later on. And so I definitely foresee a range of thermal storage technologies at different temperature ranges, as I indicated before, and using different storage media, depending on their melting points, on their sensible store, whether it is sensible storage or latent heat storage. So you can have a cascading system of storage systems, all the way from a very high temperature of 1000 degrees Fahrenheit or 600 degrees Celsius to all the way to hot water under pressure, which can be stored at 80 degrees C or even beyond the boiling point of water. But if you use other liquids such as which has higher boiling point, you can store that at higher temperatures than that, than water's boiling point. So I definitely see benefits to it, and thereby reducing the cost of this combined system, where you can use the storage to run the turbines or run the industrial system from waste heat exhausts, or from primary sources such as renewable energy sources, as we talked about earlier.
So in continuation to what Mr. Subhadra was asking, is there any scope of integrating thermal energy storage for solar photovoltaics energy generation?
So, okay, the difference between, so solar photovoltaic systems are the cells, solar cells that directly convert the solar energy to electricity. So the conversion there is, the conversion efficiencies are gradually going up. Solar cells being built more recently have 18%, 20%, and 25% efficiency of conversion. They used to be only about 10% conversion efficiency, even as late as about 20 or 15 or 20 years ago. So as the efficiency of conversion to electricity goes up, there'll be more and more applications of the photovoltaic cells. Now, if you want to convert the solar energy to heat, as in the form of storing in molten salt mixtures that I talked about earlier, or high pressure steam systems, the solar exposed surface has to be radiated by heat exchanger tubes just below the surface of the radiated surface. And that is how you convert the solar heat to thermal energy. So you can either have a solar photovoltaic system to convert directly to electricity, or a solar thermal plant, as I described earlier, where the heat exchange medium is then run through another set of heat exchangers to produce steam, if it is a molten salt system, or if it is a steam system that can be directly run through steam turbines to produce electricity in addition to the photovoltaic systems. So the two systems that I'm talking about, the photovoltaic and the solar thermals, are two parallel ways of generating electricity. One directly from solar energy to electricity using photovoltaic cells, and the other using solar thermal systems, which go through a thermal energy process conversion to electricity. Is that clear?
Yes,
Does that answer your question?
We have one more question from Dr. Lakshmipati B.
Okay.
So he's asking, how effective will the electrical storage system, since thermal energy storage has greater advantage of storing and retrieving energy?
Right. So of course, you absolutely need electrical form of storage in applications such as laptops and your smartphones and electric vehicles and so on. So obviously there you cannot use thermal energy storage, so you have to have forms of electrical energy storage. The efficiencies, of course, like I said, disposable batteries are the least efficient, because they are only used once and then they are disposed of. Rechargeable batteries are more efficient because they can be used over and over again by recharging as they are discharged. And then you have the other forms of battery where you other technologies of batteries, where you have higher efficiencies such as nickel metal hydride batteries and so on, where the efficiency of charge and discharge happens over a longer period of time, and they last longer and are more efficient and more do not lose as much charge even through the discharge and charging cycles. So in certain applications, you absolutely need to have electrical form of storage, and in other applications, you can use thermal energy form of storage and produce the same power in stationary power plants and stationary uses in industry or in chemical plants and so on, or even in ships and locomotives or transportation of other types, mass transportation. But in the case of consumer transportation or individual transportation, as in electric cars, you need to use batteries only. Or, I mean, you cannot use thermal energy storage, so you are limited.
Yes. Thank you, sir. And one more question from Mr. Anantesh Rao. Sir, I am working on wax PCM as a storage medium for late evening cooking using solar energy. Please tell me, sir, whether it is feasible for future.
Yes. So, like I said earlier, the wax system has a very limited temperature range through its melting point. So the solid wax melts at the melting point and stores heat in the form of latent energy, and till the entire solid material has melted, right? So the temperature of storage remains a constant, but the amount of heat stored depends on the amount of wax, the mass of wax in the system. So the heat is then released. In your case, you're using it for cooking when the wax re-solidifies from a liquid form to a solid form. So certainly it can be used, and like I said before, wax is the substance used. Paraffin wax is a substance used in thermal, in building envelopes or building wall material. So where the wall material is impregnated with paraffin wax in matrix form, so that it doesn't leak out or doesn't spread out through the wall material and gets lost. So they are used in matrices or in spheres, or they are even used in swimming pools and so on to undergo melting and resolidifying to heat the water in the swimming pool. So several spheres of the PCM material or the wax material, whatever the phase change material is used for this purpose, several spheres or balls of them are stored in the bottom of the swimming pool. It releases heat when the cold water comes in touch with it and warms up the water for the swimmers to feel comfortable. So you can have, and these get recharged then by either solar energy or for later use in the nighttime or evening time when the sun goes down. So these are some of the applications. I mean, they're definitely one of your applications is for cooking purposes, and there are several such applications in the, like I said, in the building wall material to heat the space, the air next to the wall. So the material melts as the wall material is heated by the solar energy from the outside, and resolidifies when it discharges the heat into the inside air, the building air, where the occupants of the building have to be kept comfortable during winter time. And then it refreezes when it discharges the heat and resolidifies. And so it goes through the melting solidification cycles as the uses are made. So I'll talk more about this particular application on Thursday morning, your time.
Sure. So we have one more question from Mr. Palani C. Is there possibility of effective thermal storage in our country? I believe he means India.
Of course. Of course there is. So of course the temperature, the climate temperature variations are much smaller in India, as you know. So the seasonal storage systems that I talked about are much less applicable because there's not the big range of winter and summer variations. Even though the northernmost climates are very cold, when there is snowfall and so on, you need buildings heated. You can certainly use underground forms of steam or hot water storage to run through the pipes of a building. Similarly, you can charge up ice storage systems in the southern climates during evening or nighttime for use during the daytime. So when the outside temperature goes up higher, and when you need the building inside, the occupants in the building kept cool, you can run the either the absorption system using solar thermal system, using solar energy, or wind power energy, or a heating plant to produce the chilled water or ice storage systems to run the cooling system through it. So the air is passed through a heat exchanger with the where the iced water is flowing on the cross banks of the tubes, and thereby the air is cooled and pumped into the building to keep the building cool. So certainly there are applications of storage systems in India, and it is commonly used as well.
So do you know any place where it is implemented in India, sir, at the current moment? So that's a continuation question from Palani again.
Yeah. So a lot of the commercial, meaning office buildings, are right now being cooled by electricity and using compressor because the efficiencies are much higher. But if you if you have a good land space and where you can install solar cells, you can certainly use solar energy to store the heat and run the absorption chiller to run, to operate the cooling storage systems. Now, the colleague, the common friend, mutual friend I mentioned of Professor Pendyala. So Satyanarayana Kuchibhatla has a company called Parisodhana Technologies in Hyderabad. They use the phase change material to design hand warmers and crib or child carrier warmers for keeping the babies warm in the nurseries and in hospitals. Similarly, so that's an application of a phase change material, for example. But when you're asking about cooling systems, you could have these systems designed and built, but I am not sure if there is a particular building example that already uses it. but they have looked at these systems in the past and may not have implemented it. One of the buildings or building types that you should look for are in college campuses and university campuses, where you can run chilled water systems or heated water systems for keeping the buildings warm or cold depending on the climate. And those are very efficient because you can run it throughout the campus.
Yes. So we have one more question from Mr. Prabhakar Patil. What are the recent research trends in supercapacitors? On what factors they may be improved further in terms of energy density?
Now that's a question for speaker later on, because we are going to talk about supercapacitor as a single topic.
Right. That's yeah. You can
Absolutely
reserve your question, Mr. Prabhakar, till that time.
Yes.
We have one more question from Mr. R. Naresh. Good morning, Professor. It was an excellent overview talk on energy storage. Can you please share your views on potential and future scope of latent thermal energy storage using phase change materials? I think we have a discussion when that's going to come up on phase change materials.
Yes. Yes. So that's why I didn't want to get into too many details in this, because this is an overview.
Right.
So I skimmed over some of the details, but they can certainly refer to some of the references if they're interested.
So one last question, sir. This is from Mr. Ramesh Vishwakarma. What is thermocline energy storage tank?
Yes. So, so thermocline is simply the imaginary line of separation between the hot liquid on top and the colder liquid at the bottom. So in a single hot water storage tank or a water storage tank, as the water is heated, the heated water rises to the upper portions of the tank, and the colder water flows down. So there's a constant circulation of hot and cold water as the whether it's a gas heater or any form of fuel is used to heat the water from the bottom. So you have the flame and the combustion mechanism in the bottom of the tank. As the water gets heated up, it rises to the top, and the separation between the hotter water and the colder water at the bottom is the so-called thermocline, or the separation of temperature cline is what is called thermocline. So instead of storing the cold and the hot water in two separate tanks, you store them in the same tank, and the thermocline rises when you heat up the tank, and then it comes down or falls as the hot water is used up, and colder water comes back into the tank.
Yes,
is that?
Yeah, I think that's fine, sir. Thank you, sir. Thanks for answering all those questions, and I once again thank from the organizing committee for giving us a broad overview of the energy systems that are existing in the market today.
Thank you.
Thank you from the bottom of my heart.
Thank you.
Thank you, sir.
You're welcome, and we'll meet again later in the week.
Yes, sir. Yes, sir.
And good luck for the rest of the sessions.
Thank you, sir. Thank you.
Thank you very much.
So, for all the participants, the attendees,